بسم الله الرحمن الرحيم. الحمد لله رب العالمين والصلاة والسلام على أشرف الأنبياء والمرسلين وعلى آله وصحبه أجمعين. رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقهوا قولي. اللهم لا سهل إلا ما جعلته سهلا وأنت تجعل الحزن إذا شئت سهلا. Assalamu alaikum and good day to all of you. So for this video, we are going to cover chapter 5, which is torsion load. And basically you have learned about the axis load before, and I already covered a bit about the torsion load. So I will go quickly for the certain slides here. So we can start now. Okay, for this topic, you will learn about basic knowledge about torsion load. Okay, I already explained in the class what is torsion, how is torsion applied in the body. Number two is a relationship between torsion load with shear stress distribution and shear strain. So you have, once you have a torsion and you have a, you will consider shear stress and also shear strain. Okay, so basically if you draw the cross-sectional area like this one, you will have shear stress like this one. For example, it should be tau. Okay, and next one is the effect of angle of drift due to torsion load. And the next one is torsion load with power transmission. So in this video, I will cover part 1, maybe until relationship between torsion load and shear stress distribution and shear strain. Okay, this is a chapter outline, introduction, torsional deformation of a circular shaft. So in this syllabus, we only cover a circular shaft, okay, only. But we will include some very simple rectangular shaft. So rectangular shaft. So this is the rectangular shaft. The above one is the circular shaft. Okay, but a very limited one for the rectangular shaft. And next one is angle of twist in elastic range. So you will learn about the you will learn about the angle of twist. Okay, so for example, here there is a A, and when we have a torsion like this way, you will have a movement of A, like A prime. So between A and A prime, we do have an angle. So we call it angle of twist. Okay. And last one is a power transmission. It is necessary to learn for the biomedical engineering student. Let's say you want to work as an engineer in industry to design something like prosthetic leg, for example, then you have to understand about the power transmission. Okay, we move to the introduction. I already explained in the class, but this one is just a quickly explanation. In this topic, we will discuss the effect of applying torsional load to a long straight member. We will consider the member to have a circular cross-sectional. Okay, so we will consider the member to have a circular only. Okay, circular only. All right, so if you can see here in the picture, you can see the left part having a tibia fibula booms. So basically, injury happened due to torsional load can cause to spiral fracture like this one. So if you learn about fracture more, I believe that you are not learning about the fracture or pathological condition in anatomy. But if you go through in the Google, you can see there are many type of fractures. For example, spiral, okay, spiral fracture, transverse fracture, okay, oblique fracture, and so on. There are many type of fracture. So basically what happened if the tibia having excessive torsional load, so spiral fracture can be occur to the bone. Okay, so the second picture showing the torsion, okay, different direction. Okay, so this one illustrating the spiral fracture because of the shearing forces happen on the bone itself. So having the torsional load, you can see the X-ray image there, okay, where you can see the spiral type fracture like this way. Okay, right. So again, the same example here is not happen in transverse one like this one, but also can be occur in the longitudinal fracture. Okay. Oh, sorry. Okay, and then due to the axial distribution of shear stress, shaft made from wood tend to split along the axial plane when subjected to the excessive torque. Okay, if excessive torque, then broken. I mean the failure will be occur. Okay, so same goes to the bone. Linear fracture of the femoral shaft will be occur as well if having excessive force of torsion. Okay, like this one. Okay, so this injury is normally happen for the sport player like rugby player, football player, basketball player, and even many sport activities like jumping, for example. Okay, so you learn about anatomy, you learn about the ligament name, ligament type in the body. So one of the ligament name in knee joint is ACL, anterior cruciate ligament. So the anterior cruciate ligament, as stated here, okay, if have excessive torsion between the femur bone and tibia bone. Okay, so this one is femur, this one is tibia. Okay, so if let's say having like this way, excessive torsion, so ACL will be on or partially on or fully on. Okay, so this is also illustrating the effect of the excessive torsional load to human body. Okay, we move to the next slide, which is torsional deformation of a circular shaft. Torsion is a moment that twists, deform a member about a longitudinal axis. So it twist like you twisting something. Okay, about longitudinal axis, the long one, the long axis. By observation, if angle of rotation is small, a length of shaft and its radius remain unchanged. So if let's say, okay, I draw it here. Let's say you have a torsion like this way, you have point A and point A prime, for example, and you can get the angle of twist in the middle here, theta, for example, I put it theta here. So if let's say the angle of rotation of angle of twist is small, for example, 0.01 degree, for example, very, very small, okay, or even 0.1 degree, okay, the length of shaft and its radius remain unchanged. So the length of shaft, which is this length, okay, this length, and also the radius here will be remain unchanged because of the small angle of rotation. Okay, you have to keep this in your mind because later on you maybe have some exercise to calculate the length, the radius, and also the angle of twist for a small angle of twist. Okay, the second picture showing you about the body after deformation. Okay, so the left part is showing you the before deformation. The right part of the slide showing you the body after deformation. So if the deformed body, you can see that the length or the longitudinal line become twist. Okay, become twist. But the circles remain circular. Okay, the circle, the cross-sectional area, every single plane here, okay, every single plane here, okay, if you cut it here, then you can see the cross-section, okay, the circle remain unchanged, okay. It's not happen if you have a rectangular shape like this one. If you have rectangular shape, then the rectangular shape will be changed, okay. Example, okay, this is an example of the application of the torsional load in daily living activities. Okay, so you have this system of generator and turbine. So the turbine coming, for example, in the river, we have a turbine system to generate power. Okay, so the water will be go through the turbine, and then the turbine will give the power of torsion. Okay, rotation like this one, for example. Okay, and we'll be rotating the cylindrical rod. Okay, and rotation will be happen and generate power. Sorry, will be transfer the load to the generator. So the generator will be generating power for electricity. Okay, this is an example of application in daily activities and daily living activities. So go to the statement, stresses and strain of the circular shaft subject to twisting couple or torques. Okay, when you have a first torque coming from the turbine here, the first torque, okay, so the other way around will be different direction. So having different direction means that we have a couples lah, okay, in statics. Okay, so subjected to twisting couple and torque. Okay, so this one is Newton's law. Okay, Newton third law. Okay, we have a couple, and then the second statement here, turbine as it torque P on the shaft. Yeah, as I mentioned here, already explained, the T, the torque, the load will be transferred along the way, okay, of the shaft of the rod. Okay, number 3, shaft transmit the torque to the generator to create an equal and opposite torque, T. Okay, and then moment that tend to twist a member about its longitudinal axis. So moment for this case is transfer or tend to twist a longitudinal axis. Okay, longitudinal axis as I draw it here. Okay, another example, if you want to apply something, you want to loosening or tightening something, we are using torsional loop. Okay, you have a screwdriver, for example, you twist the screwdriver to tightening the screw. Okay, and as I mentioned here, as I mentioned before, for the rectangular shape, the shape after twisting or torsional load will be deformed. Okay, so we go to the next one, net torque due to internal stresses. Okay, sorry. Oops. Sorry. Okay, net torque due to internal stresses. So basically, this is the thing that I already explained in the class. Okay, net of the internal shearing stresses in the internal torque equal magnitude and opposite direction to the applied torque. So internal stretching stress is internal torque. Okay, so basically, if you talk about stress, it is an internal. Okay, internal internal axial stress, for example, internal normal stress, for example. Okay, for the torque, it will be related with the internal shearing stress. Okay, so here internal shearing stress is an internal torque equal magnitude and opposite direction to the applied torque. So we do have this formula. Okay, so this is coming from the static 3D formula. So you have a moment equal to R cross F for the 3D. But for the 2D, we have FD for the 2D. So for this case, we are using 3D. So that's why we have this formula T equal to T, torsion equal to moment lah. Okay, moment. Okay. And then you simplify this one, you will have F, you can substitute with the tau A. So you learned about the tau previously, the shearing stress, okay, F over E. So you will have F equal to tau A. So that's why we have to substitute this F equal to tau A into the equation. You will get T equal to R times tau dA. So the integration is having many elements, okay, as I mentioned in the class. Okay, although the net torque due to the shearing stress is known, the distribution of the stress is not known. Okay, the net torque, okay, due to the shearing stresses is known, but the distribution of the stress is not known. So it's not similar like axial load as I mentioned in the class. So axial load having uniform stresses every single location. Okay, so I repeat again for the axial load. Let me draw 2D here. So let me change the color. So the axial load, Okay, every single point here, point here, point here, point here, point here, point here, having the same stress, stress 1, stress 2, similar. Okay, but for this case, torsional, okay, the distribution, okay, this one we call it distribution lah. Sigma 1, sigma 2, sigma 3 is distribution lah. Okay, but for this torsional distribution of the stress is not known. So will be happen, I draw it here, will be happen tau here, tau here, tau 3, tau 4, okay, tau 1 not equal to tau 2, not equal to tau 3, not equal to tau 4. Okay, so this is the meaning of this statement. So it is similar, different conditions like as you have to understand this. It is because of the formula lah, because the formula is representing the R. So higher R will be having higher torsional. Yeah. Higher R will be having higher torsional. Okay, so higher R here will be higher torsional. All right, so next one, distribution of strain stress is statistical indeterminate. So you have to refer again in the previous chapter, what is the statistical indeterminate or statistical determinate, okay, and must be considered as shaft deformation. So unlike the normal stress, due to the axial load, the distribution of shearing stress due to torsional load cannot be assumed uniform as I stated here, as I drawn here. Okay. Oops. Okay, shaft deformation from the observation, the angle twist of the shaft is proportional to the applied torque to the shaft. Okay. Sorry. So I change the color here. All right. So the angle of twist of the shaft is proportional to the applied torque. So we do have this formula. Okay. Angle must be directly proportional to the torsion. So torsion is high, angle is high. Same goes to the length. If the angle is high, the length will be high as well. The deformation of length will be high as well. Okay. When subject to the torsion, every cross section of the shaft remain plain and undistorted. So circular shaft remain plain and distorted. So circular shaft is here. So here, will be remain as it is and undistorted. Next one is cross section for hollow and solids. Circular shaft remain plain and distorted because of circular shaft asymmetry. Yeah. If the shaft is symmetry, symmetry, then the plane will be remain as it is after deformation. Okay, cross section of the non-circular, non-asymmetry are distorted when subject to torsion line, rectangular shape lah, as shown in the previous slide. Okay, this one. Okay. All right. So if you can see the figure, there are many figures here. You can see the second one having the A prime and also A. So I already mentioned before the slide, or where from A to A prime we do have an angle. So angle of twist, we call it angle of twist. Okay, so this is angle of twist. Okay. Okay, when you have the stress, of course you can calculate the strain lah. Okay, so in the shearing, the strain is not the changes of length. The strain is the changes of angle. Okay, you learn in chapter 2, strain, where we have strain in changes in length and also changes in angle. So in this case, the shearing strain, the answer will be angle, not length. Okay, not deformation. Okay, consider anterior section of the shaft. So we do have this one, okay, and we cut it into this one. So you have to imagine the interior section of the shaft as a torsional load is applied and an element of the interior cylinder deformed into a robust, as I mentioned. So robust shape will be like this one, okay, in mathematics, all right? So you have B here, okay, you have A prime, you have A, and you have O. So this is theta, and this is also angle, okay, and you can get the value of the theta later on using the equation I will show you. So the thing that I want to explain here is a rhombus shape here. So we do have one mathematical formula to get the value of each length, EO length, for example, A prime O length, BA length, and also the theta, BA prime, BA rank. Okay. All right. So let me delete this one. Okay. Hmm. Okay, it's follow that this assumption where it is a rhombus, as I mentioned to you, L P equal to R theta. Okay, L P equal to R theta, it is a rhombus. Okay, this one we get it from the equation of S equal to R theta in the mathematical formula. So if you arrange, you will get phi equal to R theta over length. Okay, and then oops. The shear strain is proportional to angle of twist and radius. So in the end of the day, if you want to decide the strain, okay, strain here, the maximum strain occur when the radius is maximum. So when we have a phi maximum, so the maximum radius we replicate with C, okay, so this C is maximum radius, okay, and of course theta here, and it can be written as here r phi equal to r over c times with phi maximum. Okay, so this formula you have to remember, okay, where sometimes we ask you what is the maximum strain, shearing strain for the torsional load, okay, and it's not necessary to remember the maximum only. You can remember about the general equation as I highlighted here. So phi equal to r theta over L. So r, if let's say the question asking you to find the maximum one, so r is the maximum one lah. Okay, if you have r, for example here r, okay, r, so r, so just substitute r into the equation, you will get the answer. Okay, so I will repeat again a bit about it, even though I have explained this one in the class. Okay, so we have shear modulus. You learn in chapter 3, okay, mechanical properties subject topic. So you have either about the modulus. So in the previous chapter 3, you learn about the modulus of Young's modulus. Okay, Young's modulus, we have equation of E, okay, equal to sigma over epsilon, okay. But in this case, because it's not axial load, it's a torsion, okay, we have to consider shear modulus, not Young's modulus. Okay, shear modulus here we have G, and G is time with phi, okay, and you have equal to RC over G phi maximum. Okay, so phi is actually in this case, it is a shearing strain, okay, similar like epsilon here. So if you have a sigma, if you rearrange the equation, you will have a sigma equal to epsilon E. Okay, so in this case, I mean the torsional case, you substitute the sigma with tau, okay, epsilon substitute with the phi, E substitute with the G. Okay, that's why G phi is appear here. Okay, all right. So if you compare with the rhombus shape, okay, so the tau must be equal to R over C G phi maximum. All right. So for the Hooke's law, okay, I already explained here. So it's similar equation actually. Okay. So the shearing stress is this formula. Tau equal to R over C times with tau maximum. Okay. So next one. So the shearing stress varies linearly with the radial positioning in the section. So if you want to calculate the shearing stress, okay, if you can see here the equation having R, okay, having R. So the stress is affected by the radius. This is the meaning of the statement. Okay, so if the radius is increased, the shearing is also increasing. Okay. Okay, recall that the sum of the moment from the internal stress distribution is equal to the torque on the shaft at the section. Okay, you have this formula. Oops, sorry. T equal to R tau dA. So this one is similar like previous slide. So we just summarize into a simple equation to get the final equation of tau maximum. Okay. So you will have a dA equal to tau maximum over C times with J. Okay, so this derivation that you are no need to remember, just understand the flow on how we get the equation of the final equation. Okay, in the end of the day, you will only apply the final equation. Okay, in the end of the day, you substitute everything into the equation. Okay, you have r square dA is equal to J. So you substitute J into the equation and you will get the final equation of tau maximum equal to Tc over G or tau equal to Tr over J. Okay, so these two equations or even one, okay, you have to remember. So you will apply in the solution later on. You want to get the solution to get the answer. So you have to apply this equation. Okay, what is J? So J is a polar. Okay, J is the polar moment of the inertia of the cross-sectional area. So different cross-section having different J. So circular, hollow circular having different J, solid circular having different J, rectangular area having different J. So the J is equal to C for the solid structure. The J is equal to pi C power 4 over 2, okay, or pi d power 4 over 32. For the hollow cylinder, the J is equal to pi in bracket C2, which is the outer radius, okay, power 4, minus C1, which is the inner radius, power 4, divided by 2. So if you consider D, it will be D power 4 minus D1 power 4 over 32. So this one, in the final exam, actually, we're giving you the formula. Okay, no need to remember, to memorize. So you only need to understand on how to get the idea to solve the problem, to find the C, to draw the stress distribution as shown here. So another things that you have to remember about the stress distribution, which is tau maximum. So you have to understand on how to draw the tau maximum distribution here. Okay, and then for the circular having this shape, I mean solid. Okay, this one is hollow. Okay. All right, similar formula like before. Just a recap back. So just including the definition of tau maximum. So tau maximum, the maximum shear stress in the shaft will occur at the outer space. T is the resultant internal torque acting at the cross section. J is the polar moment of the inertia of the cross-section area. Or polar moment of the inertia is a measure of object capacity to oppose or resist torsion when some amount of torque is applied to it on a specific area. So basically, J, you can imagine that it is an initial effort to counterback the outer forces. Okay, like I mentioned in the class, if you have a stress coming from the subject, coming from the assignment, so your body is actually internal, to counterback the stresses coming from the subject, for example. This is the analogy lah. Okay, so C is the outer radius of the shaft. So again, the J is already explained before. Okay, so I write again lah. Okay, pi. Okay, all right. Okay, before we end the part one, let's go to the example one. It's very straightforward. So I just give an idea and then you can solve it. So basically this one is simple one. So you have to find the maximum stress, which is you just apply tau maximum equal to TC over J. Okay. Okay, like this equation. So T is given. Okay, just substitute T. Make sure that the units is correct. If not SI unit, then you have to convert into SI unit. Okay, on the spot. Okay, C is the maximum one, which is 0. 0.018, and J you have to calculate lah using the formula of the inertia. The polar moment of inertia, which is pi C power 4 over 2. Pi 0.018 power 4 over 2. So you calculate, you will get the answer of tau maximum actually. Okay, you can go through later on, you can try. This one is very simple one. So example 2, also simple. Okay, the difference is only J, which is a hollow cylinder shape. You need to try. Example 3, okay, example 3 I will explain in part 2 video. Okay, I think that's all for the part 1 video. See you in the next video.